Good afternoon to all of you. Let's start with today's class. Today we are going to start with the next topic, that is microphones, amplifiers and tuners. So there's nothing in detail over here, just an overview of the basic understanding. So today's class I'm going to talk about mainly microphones. How do microphones work? You have been using microphones extensively. Remember, all the sound recording that you did was done by using microphones. They have become, in fact, a very important device in our day to day lives. So, it's very important to understand them, how they work, how to deal with them. I hope you all can hear me clearly and see my screen perfectly. So today's class we are discussing microphones. We will talk about different type of microphones, their directionality and impedance, sensitivity, etc. So these are the points that we have on the table today to talk and discuss about. If you have any doubt or difficulty, you can text me immediately. Today, after the class, we will have a Google Meet session where you can, uh, if you want to discuss, talk about anything with me, I will be available. So, what are the microphones? Microphones are basically devices which convert sound signal into electrical signal, as we are all familiar. So, for example, when you're talking to your friend on your mobile phone, then your sound signal, the whatever you talk, is sensed by the small mic placed on one end of your microphone, on one end of your mobile phone. You will see that there is a small hole there, and that microphone converts the sound into electrical signal. Basically what it looks for is sound is nothing but the variation in sound pressure or air pressure, compressions and rarefactions, and that pressure change is sensed by the material of the microphone and converts it into electrical signal. So basically the steps are straightforward. You have pressure variations in your sound waves that hits a vibrating diaphragm. Almost all the microphones have a diaphragm to which the sound waves go and hit and produce vibrations in the diaphragm. Diaphragm design is very critical. It can vary from very lightweight materials, thin plastics, from them to metal sheets, thin metal sheets which are solid and rigid and long lasting. So diaphragm material is very important. Diaphragm material determines how fast or how quick the diaphragm can vibrate, what is the frequency response, what is the amplitude, etc. etc. In general, heavier materials will not vibrate very quickly, while the lighter materials can vibrate very fast. And then that leads to the electric generator. There are different kind of microphones depending on how they impart the pressure variations to vibrating diaphragms. Depending on the technology used, they are classified as piezoelectric crystal microphones, moving coil microphones or dynamic microphones, capacitor or condenser microphone. So we are going to look at each one of them today. The microphones can be omnidirectional. Omnidirectional means they have a sensitivity in all possible directions, and they can be unidirectional. They are more sensitive in one direction and less sensitive in the other directions. So now In crystal oscillator, you are familiar with the piezoelectricity or piezoelectric crystal. If you have not read about it, please read about it again. There are certain materials. One simple example is quartz, that if you apply some pressure along one axis, is it develops a potential difference across the other axis. Now this property is reversible. So if you apply a potential difference on one axis, it generates pressure on the other axis and undergoes either extension or compressions. So when those extensions or compressions happen, then in that case, you can see that the material will vibrate and any diaphragm or anything connected with it can vibrate. So here the first property is used. What we do is, this is my crystal over here. These are the two ends to which the wires are connected. There is a diaphragm. The sound comes and hits the diaphragm. When the sound hits the diaphragm, a pressure is applied along this axis on the crystal. As the pressure is applied along this axis, a potential difference is created along the other axis. That potential difference will be proportional to the applied pressure, which in turn is proportional to the sound wave pressure. Examples are Rochelle salt crystals, barium titanate, lead titanate, quartz, etc. Typically, these produce large signal output. So if you want very strong signals, the crystal oscillators are preferred. However, their high frequency response is not flat. Flat, you are familiar. The frequency response curve should be horizontal. At high frequency, it is not that horizontal. It starts dropping, or there are some unevenness that has been observed. So this is a simple idea of a crystal oscillator. They are most expensive, by the way, of all the types of the microphones that we are doing today, typically because the crystals are expensive. Then the dynamic microphone is the familiar, just like dynamic loudspeaker. There is a coil which is kept in a magnetic field. Whenever the sound wave hits the diaphragm oscillates. That makes the coil attached to it vibrate in a magnetic field, and the flux through the coil will change. As the flux through the coil changes, an EMF is induced in the coil. The induced EMF is proportional to the voltage. The induced EMF applied is proportional to the pressure variations of the sound wave. So here is the sound wave, hits the diaphragm vibrates, magnet is fixed, this coil moves, the flux changes, EMF is induced. This is the cross section of such a device. There is a magnetic field. It's a W-shaped magnet we have already discussed. It's a cross section, so it must be it must be a cylindrical circular magnet. The cross section is W-shaped. This is the cross section of the coil. The coil is this way. This is going to be your screen or diaphragm, and the vibrations will happen this way. EMF is induced from this end, and this end wire is taken out. So yeah. So small voltage, it generates a very small voltage in the coil. Remember, it's working on the Faraday's laws, that is electromagnetic induction. But it has a small impedance also. The resistance of the wire is small, so power could still be very high. So remember, power is E into I. So small resistance will give you large current. So it could be very sensitive, decently sensitive microphone. It is very rugged, broad frequency response, and can withstand high sound level, and that is because of which it is very common to use. So most of the time, if you heard about people holding a mic and talking on a stage or in a presentation, most likely chances that the microphone that we are using is dynamic microphone. You can use it very ruggedly. I'm going to talk about the other microphone which is fairly popular, which is called condenser microphone, but it is very sensitive and has to be kept at a place ideally to be worked upon. Now, can loudspeaker act like a microphone? So for example, if I take the diaphragm of the loudspeaker and if I throw a loud sound onto it, the cone on the cone of the loudspeaker, would there be an EMF generated at the other end? Theoretically, yes, because once the diaphragm moves back and forth, the coil will move in the magnetic field and there has to be a. But would it practically happen? Can there be a scenario? Think about it. Here is the cross section of a dynamic microphone. So we are all familiar, it's out in the lab, you have used it or you have seen it at least. Typically, there is an outer shield, mesh shield, which is a windscreen. So windscreen typically kept to avoid any fan wind or any other wind hitting and the microphone inside. So that's the shield. There is the diaphragm here. There is a moving coil in magnet is at the center and the periphery. In between there is a coil, and then the wires goes out. This is a handle, the or called as housing, which actually keeps all the things together. There's an on off switch, there's a connector, cable, plug, etc. So that's how a typical arrangement looks like. Your actual sensing device is very small, placed here. The other type of microphone is the third type is condenser microphone, which is also very commonly used, very popular, especially when high fidelity of sound recording is needed. The condenser microphones are preferred microphones. So the idea here is that there is a, you know that two parallel plates connected to a battery, one becomes positive, another one becomes negative. It acts like a condenser. So what you do is you take a battery and keep the two plates charged. Now, one of the plate is nothing but a diaphragm, and the sound wave comes and hits the diaphragm. Now we know that the capacity is inversely proportional to the that is missing. Please take it. So capacity is inversely proportional to the separation between the two plates. You know that the formula for capacity epsilon naught K A by D. So C is inversely proportional to D. So what happens is when the sound wave comes and hits, the diaphragm vibrates. As the diaphragm vibrates back and forth, the D changes the separation between them, and that will change the capacity. And now, because of this potential source or battery source, number of charges are fixed. So you also know that C is equal to Q by V or V is equal to C by Q. Since charges are fixed, Q is fixed. So as the capacity changes, the potential difference across the capacitor will change. So one plate is permanently charged, other other one is the diaphragm which senses the sound waves. The spacing between the two plates changes, hence the capacitance changes. Since the charge is constant, the potential difference on the plates changes according to the input signal. So we are using the two formula. I'm not writing them here, but I mean they are straightforward. Capacity is epsilon naught K A by D. K is mostly 1, so epsilon naught A by D, which is equal to Q by V. So as D changes, V changes. So your output will become uh, proportional to the separation between the two plates, which is proportional to the sound wave pressure. It is a very low noise, that's the advantage, and it has a very extended dynamic range. Dynamic range means the frequency response is very broad, noise produced is very little, therefore you get fairly uh, perfect recording output, and that is why it is one of the very common microphones to be used in high precision recordings. So most of the studio recordings, music recordings, you will find that they are done not by using dynamic microphone but using condenser based microphones. In fact, Any stage program you will find that the microphones are handheld circular, while any recording you will find that the microphones are little flat. So those are condenser microphones. They have a very high impedance, remember, because at the input level the two plates are separated, so there is no current flowing between them. Therefore impedance is very high. High input impedance is preferred, so that way the dynamic microphones are actually the least are most disadvantageous, because in a dynamic microphone the current, the wire circuit has to be completed for the current to flow. Therefore they have least input impedance, while condenser microphones have got highest input impedance. The diaphragm also is very light in this case, therefore giving a good frequency response. The only drawback is that you need another source of power or a battery to maintain the high or constant charges on the two plates. If this battery is gone or if this circuit is not available, then this will not work properly. So that's a disadvantage. Now microphones can be omnidirectional and bidirectional and directional. Omnidirectional means it has a pickup in all directions. So many of the stage mics have got pickups from all directions, but then there are certain mics which have pickup in one particular direction. So it's very important. The omnidirectional microphones, there could be sound from all directions, and there could be some feedback issues, and there could be some oscillation issues. So in that way the directional microphones are preferred over omnidirectional, because it does not take the back wave very strongly. If it is not omnidirectional, if then I mean, look at this drawing. So for an omnidirectional the drawing is almost circular. It has a sensitivity in all possible directions. However, if it is directional, then it has more sensitivity in one direction, while you can see that the graph bends sharply in the other direction. So the sensitivity decreases. The distance, the radial distance from this circle describes the sensitivity. So you can see it drops. Typically this shape is this is heart shaped pattern, and that is why the directional microphones are also called as cardioid microphones. So please take a note of that. Typically in an omnidirectional microphones you create a hole at the back and you convert it into a directional microphone. Here are the responses of a directional microphones in many ways. So at 0 degree you will find that it has a very strong response. At 90-degree direction you can see that it has drops by 10 dB, and at 180-degree direction, if the source of sound is placed over here, then it drops by 20 dB. So it has a highly directional response for different frequencies. This is going to happen, that the response will vary for different frequencies. Can anyone tell me why? You can think about it. We have talked about it earlier. The diffraction effect will be responsible for variation in the frequency of the microphone, variation in the pickup of the microphones with frequency. So do think about it. Most of you are getting done with your project work this year, but next year you will have another long project work where you can actually revisit some of these ideas if you wish to. Microphone impedance is important. Impedance should be very high. It's preferred. Both crystal and condenser microphones have input impedance of around 50 kilo ohms and above, which is a nice one. They are expensive though, both of them. Dynamic microphones, they are cheaper, but their impedance is low, so that way it is not advantageous. Cable also helps to attenuate the microphone impedance. Long cable can attenuate high frequencies in high impedance microphones. So for example, if you have a 20 feet cable, Then at 10 kilohertz, it can attenuate the impedance by 6 dB. So long cables should be avoided. However, practically it is not always possible. For example, if there's a stage presentation, then the long cables do come in the picture. However, present day microphone technology is quickly moving towards the wireless, Bluetooth and other techniques that we are obviously not covering because the course deals with the basic structure of sounds. Another topic that we need to talk about is microphone sensitivity. Earlier we talked about the directional sensitivity, but then how do we calculate or define sensitivity? So one of the ways to define or measure the voltage sensitivity is place the microphone in a 94 dB sound field. It's a very high noise sound field. Remember, 94 dB. Go back, look at the dB scale. Around 55, 50 dB is normal conversation. This is 95. Around 80 dB, it becomes very loud. 90 dB is the output, maybe from a jet plane or something. Very, very loud. So if you place a microphone in that loud environment, why 94 dB? Because it is equivalent to a sound pressure of 1 Pascal. Then you measure the open circuit voltage, how much voltage it is generating. If it is generating a very high voltage, then it is a highly sensitive. If it is generating a low voltage, it is low sensitive. But that is how the sensitivity is rated. Uh, the voltage sensitivity is then defined as SV is nothing but 20 log V by P, where V is the voltage that it will generate and P is the pressure in Pascal, which is 1 Pascal in this case. Power sensitivity is again a direct extension of voltage sensitivity. There's nothing great here, just a formula. Voltage sensitivity minus 10 log Z plus 24, not getting into the derivation. Z is the electrical output impedance. So that's about the microphone sensitivity. So I'm showing you a small video. With the overture. I'm showing you a small video, and in this video we will cover up all the things that we have discussed today and maybe a hint to what we are going to talk about in the next class.
Carry on with the overture. Microphones. Pretty much every musician has to deal with them at some point or another. How do you actually know which one to use and how to use it? To start, there are two basic types of mics that you might use: moving coil microphones, which are most commonly called dynamic mics, and capacitor microphones, which are most commonly known as condensers. Dynamic mics are known for being rugged, affordable, and all-around useful.
Not bad at all.
They don't have the crystal clear full bandwidth operation of condensers, but this is actually often a good thing, such as when you're recording certain types of drums, guitar amps, or other acoustic instruments. Condensers are good for vocals, generally somewhat fragile, and usually more expensive. They are known for their ability to capture fine detail. Condensers require some current to work. This is phantom power, which is commonly represented by a button or switch labeled as plus 48V. Microphones are a type of transducer. A transducer is something that converts energy from one form to another. In this case, they're taking sound waves and turning them into electrical energy.
1, 2, 1, 2. Check, check.
Though different mics work in slightly different ways, they all have a diaphragm. The diaphragm is a thin piece of material, often mylar or some form of metal, and often even gold-plated in the case of condensers. When sound strikes the diaphragm, it causes it to vibrate, and this passes energy through the rest of the microphone's components. These vibrations are converted to an electrical current, which becomes the audio signal your interface uses to capture and play back the sound. Generally speaking, smaller diaphragms are more sensitive and react faster than do large diaphragms. So large diaphragm mics are often better for voice and vocals, since they don't pick up as much annoying lip and mouth sounds. Microphones have a directionality, commonly referred to as their polar pattern. Make sure your mic is pointed in the right direction. Most small diaphragm mics are known as front address, which means that you face them directly at whatever it is you're trying to record. Large diaphragm mics are commonly front or side address, which means you have to be sure you're pointing them in the right direction. One way to tell is that in most cases the company's logo is on the front of a side address microphone. Microphones create a very weak signal, so you need what's called a preamp. Your audio interface likely has at least one of them. These will amplify the very low-level electrical signal to a useful level, and it makes it possible for your audio interface to sample the fluctuating voltages more accurately. So there you go. Choose the right mic, face it in the right direction, plug it into a preamp, and then you're ready to start capturing the sounds of the world all around you.
So you got it. We are going to talk in the next class about the preamplifiers and amplifiers and tuners. So we can stop here for the day. Thank you.